Hello and welcome. In this video I want to take a look at Green's theorem, but on regions that are not simply connected. Right? The theorem states that the region has to be simply connected. However, we can generalize it because if you've got some other, come on now, if you've got some other region, let's say, that has a hole in it, right? So you want to compare the double, so you got some vector field, right, PQ, and you're gonna do the line integral around the boundary, whatever that means. We got to be careful and compare it with the double integral of something inside, right? Green's theorem was that the line integral of around the curve C of P dx plus Q dy equals the double integral over the region D, which is the inside of the C there, of Q sub x minus P sub y dA. Okay. Now, what I want to take a look at is, what do I mean by the curve C? I mean, if D is this region, is this whole region inside here, and all of this stuff in here, but not the whole, right? Then the boundary is both the curve on the outside and that curve on the curve on the inside. They're not connected together. The boundary is not connected. However, I still want to say that the theorem applies and it works, and it does so this way. So consider doing this double integral, okay, over that region, and I want to split the region up into two pieces. So I'm gonna draw a line there, and so I'm going to consider the following two regions. This is region 1. I'm going to call it D1. This is region 2. Call it D2. And I want to orient each one of those regions in a clockwise direction. Right? So D1, sorry, in a counterclockwise direction. So D1's like that, and I'm going this way around there and this way around here. So positive orientation means that as I'm walking along the curve, the interior of the region is to my left, and the exterior is to my right, so this is positive orientation. On D2 here, right, if I orient this in the positive direction, so I'm going this way around, and this way around, and this way around, and then I'm going to come in there, and in here, and in here, and back out this way. So what I notice is that if I think about this line integral around both of those boundary curves, that is the D1 boundary and the D2 boundary, that there's two pieces. These two pieces that I added in get used twice each. With D1, this gets used in this direction, but in D2, it's used in that direction. Likewise here, D1 uses that edge this way and that way. So if I just think about doing this line integral over both of those boundaries, I would add this in here, but I would subtract it out on the D2. I would add this in with the D1, and it would be subtracted out with the D2. That each of those two edges gets used in both directions, and so those cancel out. So the net result is that line integral around the sum of both of those boundaries is the same as the line integral around the outside of D and the inside of D. But notice that the inside is actually oriented what looks like the clockwise direction. Now it's the clockwise direction, but still, if you're walking in that direction, your right hand is pointed to the exterior and your left hand is pointed to the interior. So this is still the positive orientation on the inside, right? And in, Green's theorem would say that on D1, so let's say the line integral over C1 of P dx plus Q dy equals the double integral over D1 of, how's this work, Qy minus Px, no, Qx minus Py dA, right? And the line integral over C2 of P dx plus Q dy equals the double integral over D2 of Qx minus Py dA. But if I add these two together, this is just the double integral over d of qx minus py dA. And we've seen that if I add these two together, I get the integral around the boundary. These two pieces cancel out, and I just get with the line integral around the whole boundary of p dx plus q dy, with the boundary oriented positively, both the outside curve and the inside curve. So it makes the outside be counterclockwise and the inside curve clockwise. Right? And this can continue for even weirder, you could have more holes in it. Right? Suppose you had two holes. Well, just chop it like this. Oops, that one was a little long. Right? And so you have one piece that goes around clockwise like this, right? This way, this way, this way, this way, back that way. That's positive orientation. And then down here, the positive orientation does this. Again, each of the added segments that you put in there get used both in the forward and the backward direction, so they're going to cancel out, and you just get the outside curve rotated counterclockwise, and the inside curves, both of them, going in a clockwise direction. So Green's theorem would work, either form of Green's theorem, right? The circulation form or the flux form works on these non-simply connected regions as well, provided that you orient things properly, that you make those inside curves clockwise rotation, because that is still positively oriented with respect to the region that you're talking about. Okay. So there you go. There is Green's theorem for general regions.